Hey everyone, we will be discussing today intermolecular forces as well as properties of liquids and solids. Alright, so let's just get right into it. So liquids are intermolecular forces. So the concept of intermolecular forces, why do atoms or molecules hold together as liquids or solids instead of existing only as gases? So if you have all these individual molecules, right, how do we get them from being in one state to another state? Well, it's through intermolecular forces, right? So these forces are an attractive force that operates between two molecules. So there's going to be, when you put like a molecule of water and another molecule of water, there's going to be some sort of intermolecular force between these two molecules in order to attract them together to create that liquid of water. So you have H2O and H2O, and that there's a force between them. So H2O and H2O, what are those? Those are going to be covalent bonds, right? But then those two covalent compounds or molecules are going to have this intermolecular force to keep them kind of together. Now that intermolecular force that is keeping those water molecules together is going to be much weaker than the bond that's between the hydrogen and oxygen in the covalent molecule of water. So you have your bonds, which is like hydrogen to oxygen. That's a lot stronger than the force that's between the H2O molecules keeping them together. So just remember that the intermolecular forces generally are going to be weaker than the bonds, right? And you just think about it that it's a force, right? So versus a bond. So the force is just kind of this light pulling, and the bond is actually creating or sharing or exchanging electrons. So that's not necessarily happening here. It's just the attraction of the positive and negatives kind of magnetizes them closer together, but not creating necessarily a bond. So just remember that they're weaker. Okay, so dipole. So dipole moments. So when we think about dipole moments, we want to think about polar bonds. And so polar bonds are between what? Covalent bonds, right? So covalent bonds are going to have, like for instance, you have CO, right? And so when you have CO, you're going to have a partially positive side and partially negative, right? And we talked about how you have when you have this side that's more electronegative and this side is more electropositive, the direction of the polarity is going towards the more electronegative, right? So in that, there's going to be dipole moments that are going to be happening between kind of these polar molecules. So there's three types of dipole moments. You have a polar dipole, an instant dipole, and an induced dipole. So the permanent, I said polar dipole. Permanent dipole is a permanent dipole exhibited in a polar molecule due to its fixed partially positive and negative sites. So the permanent dipole is the basic polarity that we already see in a polar molecule. So this is so let's draw these in terms of, this was a molecule, right? So there's a permanently fixed spot in this molecule. So it's partly carbon and partly like oxygen. So a lot of these are my electrons. So a lot of the electrons, right, are going to be on the oxygen side because the oxygen is going to be more electronegative. But this is permanent, right? So this location of where the negative charges are is going to be fixed. So this is going to be a fixed partial positive over here and a fixed partial negative, okay? Permanent, right? It's fixed, it's not moving. So the second one is an instantaneous dipole. So a temporary dipole forms when electrons in an atom or nonpolar molecule happen to be more on one side in an instant in time, causing it to be more negative than normal and the opposite side positive. So what does this mean? So we have our permanent, right, where This is just permanently here, like this, okay? So, and that's in the permanent dipole. So then when you're talking about an instantaneous dipole, what this is saying is that it's a temporary, right? So instantaneous, so it's not permanent, is fixed, it's not moving. The instantaneous is temporary. And it's temporarily formed when the electrons or atoms of the nonpolar molecule happen to be on one side in an instant in time, causing it to be more negative. So for instance, when you have, let's say CO2, right? So this would be a nonpolar molecule, right? Because even though this is partially negative and this partially positive and this partially negative, these cancel out, right? Because the pool is equal on both sides. So they cancel out. So that would be an example of a nonpolar. So when you have a nonpolar molecule that is like this, there's going to be one side of the molecule, and here, let me write this as a molecule, right? So if we said, okay, this is, right, the negative, right? And those are my little electrons that I'm saying. That's my big molecule, so it's like oxygen, carbon, oxygen. So there's going to be a time, an instant time. It's just going to be a quick temporary time period that causes one side to be more negative than normal than the opposite. So in these intermolecular forces, that's why we're talking about these dipoles, is that these things are going to help these intermolecular forces. Okay, so sometimes there will be there can be a molecule that comes near this, another molecule that comes near this molecule that can make this negative, these negatives that are like kind of here, be more over here. Let's just say that. Like now it's, this whole thing is here. So it went from like here, so you had your two, and now they kind of came together to make one large one, just for an instant, right? Just for the time period to have that connection. Okay, so that's what the instant dipole. So it can be instantly, temporarily flipped to, or not flipped, but changed to attract more electrons to one side. So you just want to think permanent is the normal dipole that we've been talking about, right? That polarity between the two polar, between a polar molecule. Instantaneous is going to be when they form in a dipole or nonpolar molecule, and then for an instance of time, there's going to be more electrons on one side than the other. It's going to be it's going to be more electronegative on one side than the other. And then the last one is called the induced dipole. So induced dipole is positive end of the dipole exerts attractive force on the nearby electrons, causing an adjacent atom to develop another temporary dipole. So the induced dipole. So the induced is the positive end of the dipole that exerts an attractive force near the electrons, causing it to develop into another temporary dipole. So basically what this is saying is that it's induced. So if this is induced, so the instant one will just automatically flip. So it kind of by itself, it doesn't need anything to kind of induce its change, right? It's just going to automatically kind of start having one side be more negative than the other. All right, but the induced dipole is saying, so there's going to be a positively charged, or the positively in charge of the dipole of a molecule is going to exert an attractive force near these electrons, which would then cause that new molecule to flip and have or arrange itself so that it'll be attracted to that positive side. Okay, so when you have, for instance, if you had, let's say you have, let's say you have your partial positive, or let's write this way, partial negative and partial positive. So this positive end of the dipole is going to be an attractive force for other nearby electrons. So you have this like strong positive force. So let's say if you had another electron that was near here, and you had a positive or positive, negative in here, and then a positive in here, right? And so this is near this other molecule. So remember, this is partial positive, this is partial negative side. So more electrons on here, less electrons on this side. And more electrons over here and less electrons on this side. So let's say if these were near each other, basically the induced dipole is saying that this positive charge is going to induce a kind of flip and a change and which is a kind of temporary dipole of another atom. So this, let's say, so moving on up, right? And now, oh, it's near this partial positive. This partial positive is going to make it flip so that it can be negative, right? So it's kind of like these people that are like positive over here, they're just like, even though they're positive, they prefer to have more negative people around them to make them feel more positive. Right, so they like literally flip everyone around them. So if you get near these positive charges or these positive people, right, all of a sudden you're just like, wait, hold on, who am I anymore? I thought I was pretty positive too, but not anymore. Now that I've come next to this partial positive, I'm flipping to more negative. So every time that there's this partial positive, there's the induced flip from this partial negative side to go to the partial positive side. So now you have more of this action happening, right? And that's because of that negative positive attraction. Okay? So hopefully that makes sense. Okay, let's go ahead. All right, so let's get into our first intermolecular force. So our first intermolecular force is called London dispersions. So when you think of London dispersions, the one thing I first want you to think is that this is like kind of the basic forces that keeps all molecules together. So when in doubt, and you're thinking, okay, well, what kind of forces is in this molecule? Think London dispersions. Okay, so their attraction between temporary dipoles. They occur between molecules or atoms, nonpolar molecules and nonpolar molecules, polar molecules and nonpolar molecules, polar molecules and polar molecules. They tend to be stronger and for larger atoms or molecules, relatively weak forces. So you can see when it says it occurs between, so it's everything, right? So it occurs between two nonpolar molecules, two polar molecules, or polar and nonpolar molecule. So the London dispersion, you want to think to yourself that it's the thing that everything kind of has. So when in doubt, think to yourself London dispersions. So it's the attraction between the temporary dipoles. Okay. Dipole forces are attraction between polar molecules. So dipole, right? What does that mean? Each one of these molecules must have a dipole moment, which means that there's going to be a partial positive and partial negative. That's going to be creating a pool, right? If there is no pool, if there is no dipole moment, basically saying if there is no polarity that is happening in the molecules, the two molecules are not going to come together to create a dipole force, right? They must be partial negative and partial positive to create this dipole-dipole. So this right here would be an example of dipole-dipole because it is a force that is happening between this dipole and that dipole, right? So this here is a dipole, as a dipole. And remember, the dipole is just kind of another, it's kind of to say like polar. So when something is polar, it's going to have pull, right? So, and you're going to be pulling towards, the more negative side is going to be pulling. So the attraction is going to be between the partially positive side of one molecule and the partially negative side of another polar molecule. So both of them are polar. So, like I said, attraction between two polar molecules occurs when the partially positive end of a molecule attracts the partially negative end of a molecule, generally stronger than London dispersion. So London dispersion is kind of the weakest, right? That's the one that's between everything. It's not picky. London's not picky. It's just like, hey, I'm here for everyone, to help everyone just connect. Okay, and then dipole-dipole is just between polar molecules. And then our last one is going to be called hydrogen bonding. So, first thing that you should see is that the differences between all of these, or the hydrogen, what makes hydrogen bonding different is the name, right? So it says hydrogen bonding versus like intermolecular versus, not intermolecular force because it is an intermolecular force, versus London dispersion forces, or the dipole-dipole force, right? Both of those are forces. This is hydrogen bonding. So that alone is going to let you know that this is going to be a stronger connection, right? A stronger force, because it's almost like a bond. So that's how strong it is. It's a special type of dipole-dipole force that only occurs in molecules that contain hydrogen bonded to a small, highly electronegative element, stronger than a regular dipole-dipole. So, when we think of things that are highly electronegative, right, you have to think to yourself, well, what are things that are highly electronegative? Well, what's the trend of electronegativity? You decrease in this direction, right? Decrease, right? Let's think of my E. So if we decrease, the most electronegative elements are going to be the ones that are on the far right, right? If this is decreasing, this periodic table, right? Let's just say this is our periodic table. You're going to have your elements that over here that are going to be most electronegative, which are going to be generally like halogens, right? And a lot of those metals. So like fluorine and bromine and iodine and chlorine and oxygen, like those are going to be highly electronegative. So when you have hydrogens that are connected to these highly electronegative atoms, these are examples of hydrogen bonding. Okay, so and obviously they say it's called special dipole-dipole force, right? Because it's still going to have some sort of pull between the two. Okay, so those are the three. So to review, so this example here, right, this is DNA helix, right? So for all of you that are liking to go into health, this is kind of where it applies. This is kind of more of example of like biochemistry, because we're now talking about the chemistry that's within the biological system, right? So in this example that you have of each of these in this double helix, each of them are creating a bond, which is a hydrogen bond between their amino acids. So when these connect, right, these are like all of these amino acids that are connecting in pairs. And so the way that these amino acids then are connecting with each other on this like DNA helix is through hydrogen bonding. So this combination is between cytosine and guanine. So each one of those are amino acids. So between these, there's hydrogen bonding that is happening between this oxygen and hydrogen and this nitrogen and hydrogen, right? And so remember I said it's the highly electronegative. So nitrogen is going to be more on the higher end, and so is oxygen. So that's where those connections come from. Same here, oxygen, nitrogen, oxygen. Okay. Okay, so just another example. Okay, so trends. So trends in intermolecular forces. Remember, London forces exist between all atoms and molecules. So when in doubt, think London. All molecules. That's London. London's here for everyone. Okay, and then dipole-dipole moments exist in polar molecules. So that's really key to remember because it can't be dipole-dipole if there's no polarity. No dipole if no polarity. So must have polarity to have a dipole-dipole, right? Okay. Hydrogen bonds can only exist in polar compounds that contain hydrogen. So in these molecules, it's only going to be hydrogen bonding is only between a hydrogen and a highly electronegative atom. So elements that are going to be on the right side of the periodic table that are connected to a hydrogen are going to be hydrogen bonding. In terms of strength, magnitude, intermolecular forces compare as shown. So this is really good to help you remember, like, which is greater than which. So if you had molecules, and I'm asking, write these, or what are the intermolecular forces that are a part of this molecule, then you would be able to know which ones it applies to that molecule based off of this. So the London dispersions is everything. Dipole-dipole is polar, and then your strongest is going to be hydrogen bond. So this is also going in terms of strength, right? So London's weaker, polar is a little bit stronger, and then hydrogen's really, really strong. Right. So remember these three, two, fluorine, nitrogen, and oxygen for hydrogen bonding, those are going to be ones that you see quite a bit. Okay. So down here, this is also just going over the strength again. So molecules experiencing London dispersion forces only, it's going to be the weakest. And then molecules also experiencing dipole-dipole forces, it's going to be a little bit stronger. Molecules experiencing hydrogen bonding is going to be the strongest. So those are the three, and those are the things that you need to know what they are and know the difference, right? Okay. And so here's the last chart for that. So this is also another great chart that kind of breaks down all the different forces as well as the bonds. So you have London dispersion force, a temporary dipole in one molecule induces the formation of a temporary dipole nearby a molecule and is attracted to it. This happens in all atoms. So this is a very weak version, right? It's really weak. It's just kind of like nicely creates this temporary dipole, but that's very weak and not strong. Dipole-dipole force is polar molecules, which is from a permanent dipole, attract one another. So polar molecules to polar molecules. So this first one, you want to think of it, it's the forces are like you would have permanent. So in London dispersion forces, it's a permanent fixed dipole, right? But they're still attracted to each other. It's just that there's a permanent fixed one. And then this is going to be two polar bonds. And then hydrogen bonding is two polar bonds containing a hydrogen bond to a electronegative element, and another electronegative element attract one another. So polar molecules containing unpaired electrons and a hydrogen bonded to nitrogen, oxygen, and fluorine. Then you have covalent bonds, which we know nuclei of two atoms attract electrons and share two nonmetals between two nonmetals. And then ionic, cationic, anions attract one another, which is metal and nonmetal. Okay, so hopefully you are able to see or understand all of that. Okay, so now let's get into how these attractions affect boiling points. So here's like an example. So arrange the following liquids in order of increasing boiling points: CH4, GeH4, and SiH4. Okay, so you have these three compounds, and you want to arrange them in order of increasing boiling points. So when we think of boiling points, what are we talking about? We're talking about how much energy, i.e. heat here, do we need to take something from to go from its liquid to gaseous state, right? Remember when we were talking about all the different states, and we had the different charts. We had the heating curves and cooling curves. And so it's kind of started like this, and went like this, right? And so there's going to be a point of when you're going to go from a liquid or a solid to a liquid, and then from a liquid to a gas, right? And so in that you're going to have melting and then boiling. Okay, so how much heat, how much energy is needed to go for each one of these different molecules to boil, right? How much energy is needed, and arrange these molecules in order of increasing boiling points. So basically, you want to arrange them in whichever is going to take more energy to separate these, right? So first thing you would want to do and say to yourself, well, what intermolecular forces are applicable here for these three compounds? Well, we know we have London dispersions, and what is London dispersions between? Everything. So these have London dispersion forces, right? And you also want to say to yourself, what else? Right, yes. So they have London dispersion forces. So the London dispersion forces in each liquid increase as the molecule becomes larger due to more easily distorted clouds. So the larger the molecule is, the more the London dispersion forces in the liquid increase as the molecule gets larger. So the larger it is, the stronger it is. So the larger this molecule is, like this compound is, the larger it is, the more energy you're going to need to kind of separate them because it distorts the electron cloud. So intermolecular forces increase, right? Because it's a larger molecules, and the larger it is, this structure starts distorting. So then it's going to be harder for you to separate them with heat. So the energy required to evaporate the liquids increases, right? Because when it says evaporation, it's kind of also boiling, because what's happening when you are boiling something? The liquid is evaporating, right? It's changing. So the energy required to evaporate the liquid increases. The temperature needed to supply the energy increases, and the boiling point therefore increases. So the larger these elements are, the higher the boiling point. So in terms of the location, let me periodic table. Okay. So when we look at, okay, now where is, should be somewhere. Okay. So we look at C, so it's carbon, right, carbon, silicone, and germanium. So carbon, there we go, carbon, silicone, and germanium. So those are the four, those are the three compounds, right, that are connected to these hydrogens. So remember also that, like for instance, in terms of the atomic radius trend, as you go down the periodic table, what happens? The size of the molecule increases, right? So when we have when the size of the molecule increases, its electron cloud begins to slightly distort. So the more it's distorted, which means the larger that it is, the harder it's going to be to break those forces between the large atom and its bonds that it's making with hydrogen here, for instance. So it'll be kind of like, if you think about it, like this is like a distorted cloud. It's really big. So you're going to have your hydrogens connected to this distorted cloud versus if you had like this here, the small, right? So you have these, it's going to be a little bit easier to take off these hydrogens with heat. And this is not oxygen, it's just like a nice pretty molecule, smaller cloud, so it's less distorted. So in that sense, if we look at these carbon, silicone, and germanium, right, which one is going to have a larger atomic radius? Well, the trend of atomic radius is it increases as you go from top to bottom. So that means that carbon is going to have a smaller atomic radius than silicone, and silicone is going to have a smaller atomic radius than germanium, right? So then that means our answer would look like this. So GE, and we want to arrange it in increasing order. So we're going to have the least to the greatest. So carbon was at the top, so that would be the least. So CH4. CH4 is going to be the smallest, right? Because carbon was on the top, which means it has the smallest atomic radius. And then you're going to have silicone. And then you're going to have germanium. Right? Because based off of those, like how large these atoms are, right? So, and that's even proven here, right? So when you have this going from CH4 to SiGe, you see the carbon is here, the Si is here, and the germanium is here. And so as you're going, what's happening? You're increasing the temperature. The temperature is increasing, right? As you get as the actual atom gets larger, the temperature, the boiling point increases. So then if we look down at the last one, right, arrange these liquids in the following increasing order. You kind of want to do the same thing. So each one of these, right, what's something that's similar in each one? CH, right? So in that, we're not going to look at that because that's similar. We want to look at, well, what makes these things different so that we can see how they are different in boiling points. So what's different? We have, there's all the same number of molecules. They're just different molecules. So we have CHBr3, CHCl3, and CHI3. So let's look at our periodic table, right? So we have what? You have fluorine, chlorine, chlorine, and bromine, and iodine, right? So the ones we're concerned about is chlorine, bromine, and iodine, right? So because the trend goes down the periodic table from top to bottom, right, you're going to go, the iodine is going to be the least, have the least boiling point, and then bromine, and then chlorine, right? Because this is getting bigger. I'm sorry, this is going to have the least, and then the more, it's going to be higher boiling point, and then less boiling point. Because as you go top to bottom, the atomic radius increases, so the size of the atom increases, therefore the electron cloud is more distorted. So that means that this answer is going to be CHCl2 is going to be less, it's going to be smaller, and then you're going to have your CHBr2. Oh no, it's 3. And then you'll have CHI3. Okay, so based off of the size of the radius. So hopefully that makes sense. Okay, let's keep going. Okay, so this is just to kind of, once again, kind of go over these boiling points again, and based off of their size, right, of their electron radius. Their atomic radius. So each one of these is going to have, it's going to have higher increasing boiling points, right? The boiling point is going to get, well, for this one, it's going to get higher, or this one's going to be higher than this because of the size of the electron cloud, because of the size of the actual molecule. So this is just another example. Okay. Explain. We're going to do kind of like another example. So, explain why vapor pressure of water is about 0.053 atm at 35 degrees Celsius, while that of diethyl ether, CH3, CH2O, CH2, CH3 is about 1 atm at the same temperature. So why would that be, right? Like, why would the molecule H2O have this pressure, right? And this here is going to have this pressure, but at the same temperature. Why is that? Well, the first thing that you want to look at is, what are the forces that are keeping them together, right? Because that's what we're talking about in terms of the vapor pressure, right? So where is the vapor pressure coming from? From boiling. So it starts boiling, right? That's where you're going to have your vapor pressure. It's an indication of the liquid evaporation rate, right? So how that time frame that the liquid is evaporating is the vapor pressure. So diethyl ether has weaker intermolecular forces, right? So water has London dispersion, right? Because both of them have everything, London dispersion, London dispersion. Now, water has a dipole-dipole, right? Because we know water is a polar molecule, so therefore polar molecules are going to have dipole-dipoles, polar molecule, and diethyl ether. This is also a polar molecule, right? So there's a polarity that's happening here, right, between these molecules. There's polarity. So this is also going to have a dipole-dipole. Now the last one, so each one of these aren't as strong, right? But what's the strongest? Oh, hydrogen bonding, right? And hydrogen, when it's bonded to fluorine, oxygen, and nitrogen, generally. And it can also be other highly electronegative, but these are the more important ones. So in hydrogen bonding, water has hydrogen bonding, right? Because it has the H-O. So that is hydrogen bonding. So that is going to be a stronger bond than anything that diethyl ether has, right? Because diethyl ether has hydrogens connected to carbon, but nothing that's connected to a highly electronegative atom. So that's why the vapor pressure, right, which is the pressure that it takes for this liquid to change into vapor or evaporate, the vapor pressure of the water is going to be the vapor pressure of water is 0.05 atm, while that of diethyl ether is going to be about 1. So the more diethyl ether molecule evaporates, the more diethyl ether molecules evaporate at a given temperature, right? Because it's less pressure. So so diethyl ether has a higher pressure than the the water vapor, because basically this is saying so the diethyl ether molecules evaporate at a given temperature, and because they evaporate at a given temperature, which is going to be lower, its vapor pressure is going to be higher. So it turning into a liquid is going to happen quicker, right? So that's what the vapor pressure is that evaporation. So because you're going to have weaker bonds, it's going to be able to break those bonds easier and change into vapor pressure. Hopefully that makes sense. So the water has hydrogen bonding, so it's going to the vapor pressure is going to be lower because it's not going to change from the liquid to gas as quickly because it has hydrogen bonding, which is going to be harder to break apart. Okay, so hopefully that makes sense. So now, when you're thinking about which substances, ozone or O2 liquid, have higher vapor pressure at a given temperature. So when you think to yourself, when you want something to have a higher vapor pressure, you're thinking which is going to more quickly turn from a liquid to gas, or like go from the liquid to evaporation, right? So which one is going to more quickly do so? So when you have these two bonds, you're going to have oxygen, 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 and oxygen, and oxygen, right? So when you have more molecules, right, more bonds, so it means it's going to be a larger molecule, you're going to have more to increase the temperature, right? You're going to have, it's going to be more work for you to break up the molecule. So therefore, it's going to have a lower vapor pressure because it's going to take more in order for that pressure to even happen, right? So it's going to have a low vapor pressure at maybe the same boiling point if you had of O2, because O2 is going to have it's going to be easier to go from liquid to a gas because there's less force that's needed. There's less to be broken, right? So when you have O you just have these versus, so that's going to take more energy to break up versus this. And so because it's going to take more energy, this is not going to go from a liquid to a gas as quickly as this. And the constant vapor pressure is going from a liquid to a gas. So this is going to go quicker than this. So which one has a higher vapor pressure? O2. So your answer would be this, because it's going to more quickly, more readily change from a liquid to a gas. Hopefully this is all making sense. Okay, so another practice question. Practice trends in intermolecular forces. So consider the following substances. So you have CO and HF. All right, so let's go through what intermolecular forces are there. So CO has what? So we have, well, what do both of them have? London dispersions, right? Okay. And what else does CO have? Does CO have a dipole? Can that have a dipole-dipole? Is this a polar molecule? Yes, right? So we know that's going to have, so we have CO and H. So CO has London dispersion, so does HF. So is this a polar molecule, as we said? CO? Yes, right? So that means it has a dipole-dipole, right? HF is as well, so that means it also has a dipole-dipole. Now, there's only 3 types of forces, right? So what's the last force that we have to look at? Hydrogen bonding. So what is hydrogen bonding? Hydrogen bonding is the bond that's forming, or the force, the dipole force that's happening between a hydrogen and a highly electronegative element. So here, the highly electronegative element is fluorine. So we know that this also has hydrogen bonding. But does this one have hydrogen bonding? No, right? So in that, let's go back to our questions. So consider the substances. Which has the stronger intermolecular forces? Well, let's look. We know that this is the weak one. This is a little bit stronger, but this is the strongest, right? So since hydrofluoric acid has hydrogen bonding, which has the strongest intermolecular force? Well, which one has the strongest one? Hydrofluoric acid. So this one is HF. So which has a higher melting point? So this is where we're going to go back to a higher melting point, boiling point, and vapor pressure. So this is going back to, well, which one is going to easily change states, right? Which one is going to easily go from solid to liquid, gas, or liquid to gas, right? Or, liquid, or that process of liquid to gas, and then the actual evaporation of liquid, right? So out of these, what are we going to be looking at? We're going to be looking at what we were looking at earlier, like how much energy does it take for these transitions to happen. So the stronger the bonds, the harder it is, right, to separate these forces. So when we look at our compounds here, so here you're going to have the one that's going to have a higher melting point, which means that you're the one that's going to have it's going to take more energy, right? Which one's going to take more energy for it to melt and to boil and to create vapor pressure? Well, which one has the stronger bonds? Because the more energy you need more energy in order because you have larger bonds, right? So the larger the bond is, the more energy that you need in order to break it. So that means that each one of these, the higher melting point is going to be HF. And same thing with the HF here and HF here. Okay, so hopefully this makes sense because this has stronger intermolecular forces. So it's going to take more for it to begin to melt. Okay? All right, let's keep going. So let's go now on to the properties of liquids. Okay, so the properties of liquids. What are some unique properties of liquids? So, properties are related to the distance between particles and intermolecular forces. Liquid particles are much closer together. Liquid particles are not fixed. And so when they're saying they're much closer together, they're much closer together than solid particles, right? So, than gas. So gas is like all over the place. And then liquids are a lot more closer together. But they're not fixed the way a solid is. Like a solid, right? Like this pen, these molecules aren't moving, they're fixed. Thank God, because otherwise I couldn't use this, right? But for the liquid, they're not fixed, but they're a lot closer together than gas. And the common properties of liquids are density, right, which we know is mass over volume, viscosity, which is going to be kind of the thickness of the liquid. If something's if something is thicker, has a thicker consistency, right? But it's still a liquid. Like, for instance, honey. Honey is very viscous because it's still a liquid, but it's a lot thicker than just water. Surface tension, which is going to be the tension that is, or the amount of work that's required to increase the surface area of a liquid by unit amount, and we'll go into that. And the last one is the meniscus, which we kind of talked about earlier, one of those little curve when you're measuring. First, density, right? Mass over volume, that's a heart. It's a heart. So density, mass over volume. A substance, most substances are denser as solids than as liquids because their molecules or atoms are closer together. So water is an exception in that ice is less dense than liquid water. So when we think about mass, right, so the good way to kind of look at this is that when you have a solid, this is going to create, this space isn't a lot, right? The volume of the solid is not very big, right? The volume is not very big. But there's a lot of particles that are going into this little space in order to create this pen. So the mass is going to be crazy, right? Because it's really condensed. But then the amount of space it's taking up is really small. So like that's like if we said you had, the space was 2 and then your mass was 30. Or let's say, so it's like 9, right? So this is for like a solid. So it's going to have a high density. This is solid. Okay. And then for like a liquid, you would have a larger volume, right? But the amount of particles that are in my liquid aren't going to be as much as that are in the solid. So the mass is going to be a lot smaller, and the volume can also be, so the mass is going to be a lot smaller. So even if we have the same, let's say we have the same volume, right? But the amount of particles are going to be less. So the mass is less, volume is the same. So your density is going to be smaller. So that's just to kind of show you visually, like density. So the density of liquids is going to be lighter than solids because of the mass, right? The way that the particles are all stuck together. Okay. So viscosity. So viscosity is the resistance of a substance to flow. So viscosity increases, and viscosity increase with increasing magnitude of intermolecular forces. Viscosities decrease with temperature, with increasing temperature. So the viscosity, like I was saying, like honey, so that is very viscous. But when you have honey, what's happening, the reason that it's viscous is because there's going to be an increasing magnitude of intermolecular forces. So the intermolecular forces of those molecules are coming together even more, but not to the point where they're making a new bond and creating a new state. So it's still kind of liquid, but it's going to be like a thick flow that's kind of like a resistant flow because there's going to be stronger intermolecular forces that are happening in between all those molecules. So there's all these like force. So it makes it a lot thicker. Surface tension. Okay. So surface tension is the amount of work required to increase the surface area of a liquid by a unit amount. So the greater the intermolecular force in a liquid, the greater the surface tension. The surface tension decreases as temperature decreases. Okay, so when you think of like a liquid, right? You want to think of it like a liquid in space. So when a liquid is in space, like a rain droplet, it's like a sphere, right? And so that's to maximize its amount of possible connections that it could make with something else. So when it's in a sphere, all of these molecules are sitting here like all around it, right? So that's why it makes this shape, because it says it wants to be basically as open as possible to make as many connections as possible. So it creates more surface tension, right? So that instead of part of these molecules kind of being here where it's not going to be as great, it's going to create more area. It's literally the surface area. So it's creating more surface area for things to possibly connect. So when a water droplet's like in space, it just has the normal spherical shape. But then when it's lying in a container, its edge will kind of curve up. So when we're talking about a meniscus, right? So when you have your water in a container, the edges, it will no longer be in a spherical shape, right? Because normally it's in a sphere, and let's say I'm pouring my water into something, or it's droplets into a cup. Those little spheres will then take the shape of the cup, right? It will, the container, it will fill up the container, and then there will be like some sort of curve that will happen, either concave or convex. So concave, convex. The way I remember concave and convex, well, what do you do in a cave? You go into a cave, right? So you want to go concave. You're going into the cave. I don't know. So, yes. So the curve, there'll be kind of like curves as it approaches the edges. And so, in that, let's say if you overfill a cup of water with liquid, so there will be a pile. The liquid will kind of pile on top of itself until the weight of the water is greater than the intermolecular forces between the glass and the molecules. So let's say you have this tube, right? And I fill this with water. So this is the top here. So here, I'm going to keep filling my mug with water. And what will happen is that if you overfill it, there will be this slightly convex curve that happens. And so this is all water, right? So what will happen is that if you overfill it, it will create this kind of convex um, shape um, until the weight of the water is greater than that, and the intermolecular forces between the intermolecular forces holding them together. So it's going to keep doing this. So these intermolecular forces are keeping things together, and it also wants to create better surface tension. So these intermolecular forces are kind of helping this water create better surface tension, which is more area, until the weight of the actual water that's kind of at the top of this concave is heavier than the force that's keeping them together. So once it's heavier, that's when it kind of will overflow, right? Because the water is like, oh, it's too heavy. But the intermolecular force is making it that little concavity. That's what's keeping it together, is the intermolecular forces, until the actual weight of the water makes it overflow. Okay, so so in this concept is also coming from the concept which we call adhesion. So adhesion is so adhesion. So this is something that I do want you to know. It's just not on our PowerPoint. So adhesion is when molecules of an object are attracted to the ones in the molecule due to IF means intermolecular forces. So what does that mean? So the molecules. So when you have a piece of glass. So this example that I was talking about with the water, right? If you overflow it, you might have, if you fill it up, you're going to have this convex, right? This little convex area until the weight of the water is greater than the surface tension. So that is going down into meniscus. So this adhesion is basically also part of the reason why that convex of the surface happens, because basically what happens is that sometimes the surface occurs when the intermolecular forces between a liquid and glass are less than the intermolecular forces among the molecules. So here, the water is filling up past the glass because the intermolecular forces are greater in the actual water molecule than the intermolecular forces between the water and the glass. So there's going to be, because everything's molecules, right? The glass itself is molecules, and so is the water. So sometimes there's going to be intermolecular forces between the water and the glass. So when that happens, if the intermolecular forces are greater between the molecules, right? So if this force is greater than this force, so if this force between the molecules is greater than the force between the glass and the water, then you're going to have a convex. And if your force is greater between the glass than the water, that's where you get the concave surface. So each one of these concave and convex are both considered meniscuses. So that's the meniscus that we generally look at, right? So when you have your, so when we're measuring things, right? And we would say we want to look at this here, right? And we will look at that lowest bottom area. So so now we're kind of talking about like, well, what's happening here? Why does it curve up on the sides? Well, what's happening is saying that the intermolecular force between the glass and the water is greater than the intermolecular force between the water and the water. So because of that, this is going to go higher on the edges where the glass is, because that intermolecular force is strong. So it starts to spread out and get closer to the glass because it has a stronger intermolecular force. Okay, so hopefully that makes sense. And then the surface tension, just remember that it's the greater the intermolecular force in a liquid, the greater surface tension. So the stronger that these things will be kind of together and create increase the surface area of liquid. So that the surface tension is to kind of increase surface area, which is due to the stronger intermolecular forces. Okay. So, like I said, water droplets have a spherical shape that minimizes their surface area. Okay, meniscus. So this is kind of what I was just talking about. You have a concave and convex meniscus. The concave surface occurs when the intermolecular force between the liquid and glass is greater . Less than. Okay, I still can see it. So when the concave and convex. Okay, so like I was saying, when I think of concave, I'm going to go into the cave, so it goes down. So that's how I remember. And convex, it goes the opposite, it goes up. So the concave is when there's the intermolecular forces is greater between the liquid and the glass, and convex is when the intermolecular forces is less than that of the intermolecular forces that are happening in the liquid itself. Okay. So now we're going to move into solids. How do atoms or ions fit together to make solids? And how does their arrangement affect their properties? So, amorphous and crystalline solids. So with the solids, I just want you guys to understand what each one of them are, and just kind of the differences between them. That's the more important part of the solids. So amorphous crystalline solids. So amorphous solids occur when the temperature of a liquid drops rapidly, resulting in particles solidifying in partially disordered states. Solids become soft as temperatures increase. So when we think of amorphous solids, so it's like a disordered state, right? So when you have the letter A in front of something, that generally means without. So amorphous is without. Morphous is like a structure, so without structure. So this occurs when, let's say the liquid. So if something, any type of liquid, you have like mercury or any type of anything, rapidly drops, and the structure, the way that the solid that it now formed created this disorganized structure, right? So that's what it is. It's like a disorderly state. And the crystalline solid is going to be the ordered. So crystals, you want to think crystals are in order. You order your crystals, and then amorphous is without order. So the solid does not become soft even if its temperature increases, but it will melt at its melting point. So with the solid, it doesn't become soft because it's in this very rigid structure. And this amorphous solid is solid can become soft when increasing temperature because it's all jagged, right? It's not in this perfect crystalline structured state. Okay, crystals and crystal lattices. Crystal, an orderly repeating 3D assembly of fundamental particles, atoms, molecules, or ions. So we kind of talked about this really early when we talked about liquids and solids. So crystals are just another way, another structure of the setup of some of these particles in solids. So it's a 3D assembly that's very structured. So we just talked about crystalline, right? So crystals is kind of like similar because it's still in the same family. So the crystalline structure is orderly and it's repeating. So you're going to have things that are consistently, right, repeating themselves and connecting, right? It's like very ordered versus others, which is not going to be. So the crystal lattice is a crystal structure pattern formed by repeating arrays of crystals. So this is just saying that the crystal is going to be repetitive structure, and that generally is going to be in this crystal lattice structure, which is going to create this very rigid, organized structure. So these are crystal lattices. Okay, examples. Okay, so the type of crystalline solids. So there's 4 types of crystalline solids. Okay, 4 types of crystalline solids. Okay, so you have your metallic solids, ionic solids, and molecular solids. So the types of forces holding the fundamental particles together help explain the particle properties, which are melting point, hardness, and malleability. The stronger the force holding the particles together will change these things. So these are the 4 types of crystalline solids. And remember, the crystalline solids are a very structured array of particles, okay? So this is kind of all, these charts are always the best thing to go back to refer to so that you have everything on one page. So metallic is generally fundamentally particles, is atoms, ionic, cations and ions, molecular, polar, and network is nonpolar molecules and atoms. And I'm just going to talk about, I'll just go through that. So the attractive forces, attractions between nuclei and delocalized valence electrons. So things, valence electrons, right? Which are the electrons in the outermost shell. They've been moved around. And so there's going to be attraction between those. And the ionic, you're going to have the normal ionic bonds. The molecular, you have the dipole-dipole forces. And then in the network, you have London dispersion forces as well as covalent. And they mention London because that's one of the larger bonds or forces that is happening here. Okay, so yes, and then this just goes going into the properties and then examples. But I'm not going to read that because we're going to break them down individually. So first you have solid consisting of metallic atoms, which is a metallic solid. Attractions between atoms of a metal are delocalized, and therefore it's easy to move atoms by applying force. So valence electrons move freely through all parts of metal. So they're ductile and malleable. Alloy forms when a metal is mixed with one or more additional metallic or non-metallic elements. So that would be the reason they have this here as an example of alloy. So when you have your penny, right, your penny is an alloy metal, so which is just basically a mixture of all of these different metals. You have copper, zinc, and brass, right? So those are all of the things that make up all the different metals that are on a penny, which would be considered an alloy. And that would also be a metallic solid. So you want to think to yourself that when you think of metallic solids, that the attraction between the atoms of the metal are delocalized. So the valence electrons are able to kind of move. So you're able to actually move these freely. So that's what you want to think of, that they're easily moved to atoms when you apply force. So when you're applying force, it basically has a little bit more space to allow them to kind of change, right? So because their valence electrons are delocalized and therefore it's able to create more force on that atom. So it's like all these electrons kind of like moving, right? They're like delocalized so that there can be more space. So that's metallic solids. Ionic solids contain cations and anions arranged in a crystalline solid. So just remember, the crystalline solid just means that it's a very structured 3D structure. Electrostatic forces, which is the ionic bonds, hold together ionic crystals. So they have a high melting point and they're hard and brittle. Solids are not electrical conductors, but melted or dissolved, they can be good conductors. Right. Okay. So you just want to remember that, right, that ionic solids are basically ionic bonds that are creating this crystalline structure, and that they're held together, or that they have high melting points because they're that ionic bond, right? So it's going to be a lot to take them apart. And so that makes them hard and brittle and not conduct electricity unless we get rid of their rigidity. Okay, so molecular solids. Molecular solids are solids consist of molecules held together by intermolecular forces. So you have your non-polar solids and polar solids, right? So we know, we just talked about this. So non-polar solids are going to be held by London's portions because they deal with everything. They form soft crystals with low melting points and electrical insulators, poor conductors of heat. Right, so because they have a low melting point, because London dispersion forces are not strong forces, so these are held together really weak. So that's why that they have a low melting point and they're soft. And in that sense, they can be more malleable, which makes them can be more electrical insulators, and they're also poor conductors of heat because of the way that they're put together. And polar solids are held together by London dispersion forces and dipole-dipole forces, right? Because they're polar. So any polar molecules are going to have dipole-dipole forces holding them together. They're typically harder because of that dipole-dipole force than the nonpolar, and low to moderate melting points because they have higher forces, right? So there's going to be higher melting. And the electrical insulators because there's no ions. So hopefully that makes sense. So now the last one that we have is called network solids. So network solids are consist of giant molecules of metalloids or carbon that forms the entire crystal. So when we talk about metalloids, right? Remember, there's like a little area that's between, here, let's look at it. So this area, network solids, consist of a giant molecule of metalloids or carbon that forms an entire crystal. So this area here, this little dark area, those are the metalloids. So basically a network solid is going to be containing these metals here, right? That's the kind of between the metals and non-metals. Or basically like a diamond. So a diamond would be a whole bunch of carbons connected together that form an entire crystal. So they're poor. It's a girl's best friend, by the way. Poor electrical conductors, right? And they have high melting points because they're really strong. They're very hard, so because they have high melting points, and have very stable 3D structures. Their strong covalent bonds connect atoms in a network solid. So these are really, really strong bonds. So you just want to think about a diamond, right? That's a very strong bond that's keeping it together. So diamond would be an example of a networked solid. So just remember that it consists of molecule of metalloids, which is just in that line, or a carbon that forms an entire crystal, which would be diamonds. Okay? All right, and that is all for chapter 10. All right.